Hi, welcome to the video solution guide to problem number 5 of the Tendon Design Problems Lab. In this problem, we're asked to design a tendon that meets three requirements, and this tendon is used for an ACL replacement surgery. So this tendon has three requirements. The first is that the length must equal 0.03 meters or 3 centimeters. It must be able to stretch no more, that's a weird way of saying that, the maximum stretch that the tendon must undergo is 0.001 or 1 millimeter with a force applied of 1,000 newtons. And the third requirement is that it must be able to withstand a 2,500 Newton applied force without injury. And we say that injury occurs when the tendon strain is equal to 8%. With the first requirement, with requirement number 1, that the length must equal 0.03 meters, the only other way we can design this tendon is by changing its cross-sectional area. So that's what we're going to be modifying in this problem so that it satisfies part B and parts C, so we know the length already. The first thing that we should do is figure out the area for the second requirement, so the requirement to withstand 1,000 newtons without stretching more than 1 millimeter. So we're going to use our equation where the force applied to the tendon is going to equal the tendon stiffness times its change in length, where the tendon stiffness is equal to the modulus of elasticity times the area of the tendon divided by its starting length. So expanding our first equation here, we see that the force is equal to modulus of elasticity times area divided by length times the change in length. For this problem, we're solving for A, so that's the other parameter that will allow us to design this tendon. So let's go ahead and reorganize this equation. If we multiply both sides by L, divide by the change in length, and divide by the modulus of elasticity, we'll isolate A. So rewriting this, we have the area, A, is equal to the length of the tendon times the applied force divided by the change in length multiplied by the modulus of elasticity. All of those values are known, so we can plug them in and solve for the area. So the starting length is equal to 0.03 meters. The applied force is 1,000 newtons. The change in length is equal to 0.001 meters. And the modulus of elasticity is equal to 1.5 times 10 to the 9 newtons per meter squared. And when we multiply and divide, we find that the area of the tendon needs to equal 0.00002 meters squared. So this gives us the cross-sectional area of the tendon so that it meets requirements A and B. What's left is to design the tendon, or to figure out the cross-sectional area so that the condition C, the third condition, is also met. Before we use the equation that we solved for, this equation here, before we are able to use that equation, we need to figure out what a strain, an 8% strain, is in absolute terms, so the change in length of the tendon relative to its total length. So we know that an 8% strain, or we know that the strain is equal to the change in length of the tendon divided by the starting length. In this way, we can solve for the change in length. So the change in length of the tendon is going to equal 0.08 or 8% times its starting length, and the starting length is 0.03 meters. And when we multiply that out, we find that the change in length of this tendon without the tendon incurring an injury can be up to 0.0024 meters. At this point, we're able to go back and use our equation where we solved for the cross-sectional area to figure out the cross-sectional area of the tendon so that it withstands that change in length. So the cross-sectional area of the tendon is going to equal the starting length, 0.03 meters, times the applied force, this time it's 2,500 newtons for the third condition. We're dividing it by the change in length, which we just solved for, 0.024 meters, multiplied by the modulus of elasticity, which is 1.5 times 10 to the 9 newtons per meter squared. And one thing that we should do, and what I should have done before, is done a unit check. So if we cross off our units that cancel each other, we're left with meters squared on top. And that makes sense because we're solving for the area. And when we multiply this out, when we multiply and divide, we find that the area for the cross-sectional area of the tendon to satisfy the third condition is equal to 0.000021 meters squared. So now we're left with two possible options for the tendon. We're asked to design one tendon, not two tendons. If we pick the cross-sectional area of the tendon that satisfies only the second condition, it won't be strong enough to withstand the required strain given the 2,500 Newton force applied in the second condition. Conversely, if we select the cross-sectional area that satisfies the third condition, the tendon will be strong enough automatically to withstand the strain or the change in length required in the second part. So our ultimate answer for the solution is this one, that the cross-sectional area of the tendon is equal to 0.000021 meters squared. And there we have it.